So we are going to discuss about a very important area, which is beyond the cloud. As all of us know that with the passage of time in the past 15, 16 years, the cloud has emerged as the mainstream computing platform where a lot of enterprises and individuals, they move their computational needs over cloud, especially the enterprises. They have moved their in-house infrastructure or the new computational needs or demands over to the cloud. Cloud brought many new opportunities, and along with that, there always come some challenges as well. And the cloud computing has been one of the mainstream research area in the past 20 years, and with the passage of time, there emerged new areas as well. Like cloud started gaining momentum in 2010s, and then in the mid 2010s and late 2010s, we got fog and edge computing as well. And now, with the culmination of AI technologies, there is a strong integration across different technologies. So for that reason, the things that have become probably more complex as well in terms of research and the new opportunities as well. So if I generally say or talk about this, it's not about the cloud, it's about the advanced computing, how the computing is done these days, because most of the computation right now is done on remote infrastructures onto the cloud or other infrastructure, or even if it is on the enterprise infrastructure, still it's like a massive infrastructure. So there are a lot of similarities what we talk about a cloud that are equally applicable onto your local infrastructure as well. So we'll talk about this. You can register for the Colloquium. We will talk about a little bit evolution of cloud, but then we are going to talk about research trends. And in research trends, we are going to talk about different types of trends. We are not going to talk specifically about the core cloud computing, which consists of like middlewares and the scheduling and orchestration. We will talk about the other enablers as well, so that we can have an hour orchestrating and a 360-degree view of all the different research areas which are emerging. And then challenge and implication in the future vision. Mainly we'll be focusing on different research trends. An important thing about this talk is that I have tried to have a 360 view, like a lot of areas I'm going to discuss into this. So I'm not an expert of different domains. Specifically, my area of research is in the scheduling or the middleware domain of the cloud computing. So I primarily work with that, but and the security aspects as well. But we are going to talk about a lot of other aspects as well, particularly, like with the emergence of AI and recently with the large language models, there are a lot of new opportunities and a lot of new challenges as well. So if you talk about the cloud computing initially came as a disruption, and once it became a disruption, it gave a lot of opportunities and a chance to the enterprises and to the individuals that they can move their infrastructure onto the cloud and make it very easy to use and convenient to use and easily scalable. And it brings a lot of other features like very low upfront cost, low capital investments, and ease of scalability and almost unlimited scalability, what the cloud providers usually promise. So it created a lot of opportunities. But if you look at the cloud in isolation, these were the factors. Okay, you can, instead of doing computation onto your own infrastructure, you are moving it onto the cloud. But with the passage of time, what has emerged, it was like IoT. The main enabler in the success of IoT was the cloud computing, because with the IoTs, okay, these IoT sensors and IoT devices, they do some sort of sensing and then do some sort of a computation, but most of the time they are backed by the cloud platform or some centralized platform where they send their data for computations or for analytics or for any other sort of work. And then we got many other technologies as well. Right now we are at the explosion of many other things, like we have now a lot of AI driven workloads. We got edge and IoT systems. Then we have sustainability concerns, and then security and trust challenges. These are the major areas which are really right now connected with the cloud research. If we talk about the cloud research, these are one of the major areas which are getting benefited, but also opening the doors for the new researches as well. We know like edge and IoTs are there now since long, especially IoTs. We use a lot of IoT devices. Once these fields they emerge in the early days, it looks okay, yes, there is a disruption, but initially we do not see its physical form or the things happening in the real, but gradually they start coming. And right now if you see, we use a lot of IoT devices. Even this air conditioning is an IoT device, because it could be connected to the internet and sending the data over there as well, or you are operating it remotely as well. Then we got edge. There are a lot of use cases for the edge computation, where you do your computation over the network edge or in the fog. I hope like everyone is familiar with the edge of fog computing. Edge computing is the computation at the edge, like it could be done on your home router or even on the devices like on the mobile phone. Like there is a camera which is a sensor, and then you're doing computation onto the mobile phone, and then you're probably sending this computation to the cloud for anything, for aggregating the data, or for some analytics, or for doing some other sort of decision making. It could be anything. So and then this computation can be done somewhere in between edge and cloud. So that sort of computation is called fog computing. So there is a very thin line between edge and fog computing. And then AI driven workloads. AI is there since long. I mean 70s, 80s, since 1970s, 80s, it's there. From 2000s, it started gaining some momentum, but in the past 10 years, it got a lot of momentum. And we have seen a lot of AI enablement, AI-driven applications, and a lot of work being done. But if we look at in the past 3-4 years, a real disruption came with the large language models, like with the GPTs and all this. We got some sort of a disruption, which has enabled and opened many new opportunities for the users. Now we can do a lot of things with a lot of ease, which were not probably possible a few years back. So it's giving us a lot of opportunities. But at the same time, AI-driven or AI-enabled applications, they have their own requirements as well. Particularly, it comes in terms of infrastructure, because if you want to run the AI workloads, you need to have required infrastructure, and the main thing in infrastructure that comes is the processing requirements. So you do have certain processing requirements to train your models and then do the inferences and all that. So for that, we were used to have GPUs, like graphical processing units, but the demand got increased, and then a lot of new research being done into that area. And now we have tensor processing unit, we have neural processing units. So we have a variety of types of processing available to accommodate this specific AI-driven workloads. But AI has brought a lot of new challenges as well. So remember this thing, like AI is not only a disruption, but it has brought a lot of other challenges. Like I said, the computational requirement. The other challenge is actually related to sustainability concerns as well. Because, okay, you are doing AI computation. Cloud was very good in terms of sustainability. With the sustainability, I'm talking about the green computing, energy consumptions, and carbon emissions, all these things. But with the cloud, we got an advantage, like instead of every company or every enterprise running hundreds of thousands of servers, now they are using the shared servers. And eventually the net requirement or the aggregated requirement for all these servers has been reduced, because now they are sharing the infrastructure. But with the AI emergence, again, there is a huge spike in terms of demands for the hardware infrastructure and these servers. So that has really raised concerns about the sustainability as well. And then since the cloud infrastructure is shared and cloud claims to provide a lot of security, and yes, it's quite secure as well, but still the security, trust, and privacy concerns, they are always there. So these are very important areas which you can see and you can discuss. So even in many cases, if you talk about the cloud architecture, which was a centralized large data center, it might not be applicable in many use case scenarios. Like we're talking about edge computation or even edge AI as well. So this is how the cloud computing got evolved. In the early phases, there was virtualization in the data centers. We got the things virtualized, and we started building the data center. Then we started renting these data center resources as infrastructure as a service, platform as a service, and software as a service. This is the area, the growth phase, where the cloud computing terminology actually got established. It's around mid 2000 to late 2000s, where we got this growth taken place. And then right now we are living in this era where we have hybrid and multi-clouds, and we have cloud native application, because early days you were used to have independent applications available onto the cloud. Then we started having a lot of integration among the cloud, and then we started having a lot of development onto the cloud, like cloud-based development, cloud-driven development, and deployments onto the cloud, which started actually emerging some very specific area like DevOps. DevOps got emerged mainly because of the cloud computing, because it made the operations very easy, and now any professional or anyone can manage the infrastructure with ease. So the role has been shifted, and a cloud developer even performs or an application developer actually do some sort of operational tasks as well. So the DevOps is actually it got a lot of momentum because of the cloud computing. Similar is the case with the service-oriented computing and these lightweight component-based development, or your microservice architectures. So all of them, they got momentum because of the cloud computing. So this is the era where we have been living, and now we are moving towards this era, because now AI is there, AI has been integrated, we are gaining a lot of advantage from cloud to enable AI application, but at the same time, cloud itself now needs the AI as well to run the cloud workloads, or to run the cloud infrastructure, or once you are going to build large-scale applications, because once you build an application, large-scale application, it's not relying only onto the cloud infrastructure. It might be consuming, or it's spreading across some IoT, it's spread on some edge infrastructure, and then might be utilizing some cloud infrastructure. So it brings a lot of other challenges, and those challenges, they are related to all these areas like sustainability, the energy consumptions, and all this, and then security, privacy, and a lot of other areas, they are interconnected with this one. So now we are having autonomous, intelligent, and distributed clouds. We are talking about that. So key forces, like I said you before, which are now shaping the future, they are artificial intelligence and machine learning, and there are a lot of advanced models. Then edge and fog computing, security, privacy, and trust issues, new hardware and architecture. Now they are emerging very quickly. If you look back about a few years, like if you go back almost a decade ago, in terms of hardware diversity, the pace was very slow because the need was not very high. There were traditionally CPUs, and we were having a few GPU models, which were used for only specific use cases. But now, with the emergence of AI workloads, a lot of AI workloads, there is a huge need now to have these new hardware and new architecture. It's not only about the hardware architecture, we are also talking about the software architecture and how your software is constructed. For example, if we talk about an AI model, how an AI model is working. It might not be only a centralized model, like you do have federated learning models. So you might be running your federated learning model onto different devices, onto a cluster, or onto the edge devices. Then there are sustainability and green computing issues. So they are very, very important issues. And right now, we're living in an era where we are already getting affected from environmental hazards, which are causing by these things. And like I said to you before, with the emergence of AI, this has again unfortunately been accelerated because we are using a lot of energy consumption. And with the energy, what's the problem? One of the major problem is like the energy that we are consuming to run these data centers or to run these servers. It's coming from consumable energy sources, which emits actually carbon, a lot of carbon, which damages our environment. The other thing is, it's not only about running these infrastructures, it's also about cooling down these infrastructures. So talk about the cooling requirements and other stuff. So they are also requiring energy as well. And they might be emitting substances which are hazardous for the environment as well, and they emit actually. Like if you remember, like with the air conditioning, a few years ago, we were used to use a gas which was the major reason for depleting the ozone layer. So these are the challenges which are actually being caused. And then there are societal, ethical, and regulatory pressures as well on these issues. So the first thing that we will talk about is the cloud native intelligence, like how we are going to bring intelligence within the cloud as well. We can have AI driven orchestration. You know, cloud is the biggest infrastructure, whatever you can have is, because cloud has so many layers. There is cloud data center provided by the cloud provider, and the cloud provider needs some sort of intelligence to run that data center and make the things easier for you. Why DevOps? Because the cloud has taken that responsibility of operations onto its shoulder and giving you those services to use it with a lot of ease. That's a major key for the cloud service. But that brings a lot of challenges for the cloud provider itself, like how to do these things and how to make these decisions. So resource management is very critical. So you can involve AI in doing the resource management related decisions. Similarly, stands for the scheduling and auto scaling, like how you are going to do the auto scaling, because right now we do the auto scaling based on some fixed parameter. Like we do it, okay, let's say if your CPU utilization gets to reach to 60% utilization and 70% utilization, you are going to add another instance of computation, let's say. And these decision making, they are reactive, like they react based on a certain event. But with the AI integration, you can do a predictive or proactive decision making. Like before it reaches to that level, you already predict that thing and proactively increase the scaling as well. And you know, that's the problem with the reactive, because with the reactive, you do not let your system go to reach 80 or 85% of utilization. You have to keep a margin. You do it at 60%. That's a challenge, because what about if it does not go beyond 65%? You keep now utilizing 2 instances of the same thing, because you have to do that. So with the predictive or proactive scheduling, what you can do is you can make your instance ready and can launch it instantaneously once you see that, okay, yes, it's now reaching to that thing. And if you later on predict, you observe, and especially if you're doing reinforcement learning, you're learning through that thing, and then you are getting your feedbacks back, you can later on decide, okay, I have to take it down. Then fault prediction and recovery, you are already doing when the fault is going to happen, you are predicting that thing, because disaster recovery is very, very important in the cloud provider. Cloud providers have very strong SLAs. Okay, because for example, if I talk about Amazon gives you a very, very high reliability, 99%, 999%, depending upon the service that you are talking about. Okay, so if your service goes down, so they are responsible for that, and they could incur some business losses as well. So you can work onto these things as well. Then shift from rule-based to learning-based cloud control. So instead of rule, like the example I gave you before, like you're doing it on the rule, you're saying like, okay, if my consumption reaches to this level, then do this, and if it goes below this, then do this. Instead of this, what you are going to do is learning-based cloud. You learn, you train a model, and then you are predicting like what is expected to happen. So you are proactively acting according to that. And then concept of self-driving cloud. So with all that, you're doing self-configurations. The configurations, they are automatically be done. Self-healing, if an error is occurred, so you are doing the self-healing, trying to adjust with the environment, reinstantiate, reboot your instances, then self-optimizing which one is good for me. For example, there is one very important aspect with the perspective of the cloud provider. You know, like the cloud provider tries to give you an illusion that there are unlimited resources available, whereas they are actually limited resources. So what they have to do is they have to aggregate that resources. Okay, there's a concept of Goldilocks in journal, you must be knowing that, which means like you are going to hit the exact requirement, which is very difficult in real world. And for any case, like you're going to know like how much is the exact actual requirement of my job or my thing. So it's very difficult for a cloud provider to actually predict like how much workloads are going to be required by my users. Okay, now they have to employ these machine learning models. So they are going to predict these things. Okay, and what they can do is Another problematic area is like they assign these virtual resources onto physical hardwares. Okay, so they have the virtual machine, say, and then they have to deploy them onto infrastructure. So they deploy them in some pattern. So they know, okay, the first one will go onto this, the other one is going to be onto this, and the third one is onto that, and into this region, into this data center, onto this rack. This is what they have to decide. So what they can do is they can imply the reinforcement learning, and they simply learn by deploying them, then relearning, and then adjusting their future policies as well, rather than having a static policy. So you do have, if you want to work, so you can have ML-based workload predictions, where you are going to predict your workloads in advance, because on the cloud, every user, whoever is there onto the cloud, in many cases they do have some peak hours, some peak requirements, and then they do have some off-peak hours and off-peak requirements where whereas the cloud provider, they have to know about those requirements and they have to adjust accordingly. So that's a challenge for them. So like I said, you can use reinforcement learning for resource allocation in particular. Like if you are going to assign a resource, how you are going to assign that resource, which computer, which physical machine you are going to deploy your workloads. It could be a bit easier for, let's say, virtual machines. Okay, you are going to run them in parallel, and it also depends upon the type of the workload a user is running. For example, if you talk about a workload which is like web servers. So in case of the web servers, they are independent web servers. They are serving their customers. So you can deploy them on sparse locations. But if we talk about running an application, which is a coordinated application, which is running in parallel onto multiple nodes, and they are coordinating with each other, so it's better to run them on nearby nodes. Okay. So your reinforcement learning model, they can learn these patterns, and then they can assign the future workloads based on those learning. Same is could stand for the energy optimization as well. Like which areas are good for energy optimization, like which resources are good for energy optimization, which type of workloads could be good for the energy optimization. It can be from a very abstract level to a very drilled down level, like which resource could be good for energy optimized for a workload, like for a certain type of workloads, or for certain workloads from a certain user. Similarly, you can apply it at a very abstract level, like which data center I'm going to run this one, which data center is good to have energy optimization, and then even for the green computing as well. Like you can move your workload from one data center to another data center based on the green energy requirements, because our data center could have more access to the green energy. Or it's lying in a region which is more based on green energy, like they are using a lot of renewable energy resources, whereas there is another data center which is using a lot of consumable energy resources. So you might have an inclination to run your workloads onto there. Then AI assisted DevOps. So you are going to have some AI assistance in doing the DevOps as well, because once you are doing the DevOps, you could create problems, because once you use the AI has itself its own challenge, because AI could create data drifts. It can create noises as well, because cloud want to have very sustainable decision making and very predictive decision making, whereas AI decision making can be quite unpredictable, and that's a challenge with the AI based solutions as well. So once we talk about, okay, you can bring this, you can bring that, but the other problem is like you can bring a lot of challenges associated with the AI as well. And then you can have anomaly detection with the DevOps, and then the self-healing. Then you can have serverless platform for ML training and inferences as well. Like you can have, you can use containers, and on the containers you are going to run federated learning models, or you can build new models as well, which runs in parallel, and you do the parallel computation and then aggregate those models into one, and then give your results. because you are having this challenge of the availability of parallel processing. What a GPU does sort of parallel processing. Okay, but at the instruction level, and it does the parallel processing, but the GPUs are not available everywhere. So what you have to do is you can run it with the containers or with the other serverless architectures as well. There are a few other open challenges, like once we talk about, I said it before, okay, we are implying the AI into our decision making, then what about the explainability of the AI as well? Are the decisions which are being made, they are the right decisions? So these are very open research challenges recent, because we are talking a lot about the explainable AI. So the same stands for the cloud as well. With the cloud, like I said, it's very tricky, because AWS cannot afford to lose their customers because their platform hasn't done the right decision making, and the customers, they got affected in terms of their business or other problems. Similarly, stability and safety of learning-based controllers, like how much stable they are. Data drifts and concept drift in production system. You have developed a system and there is a data drift into that. And then trust and accountability in autonomous cloud operations, because you are doing decisions based on certain parameters. And then if you are employing multiple parameters, for example, you are running the workloads based on the green computing, okay, now there could be a problem, because you are saying, okay, that data center is better to run your job, but what's the problem is that data center is far from the users of your customer. Now the latency is going to be increased, so that's a problem. You could actually breach your SLA as well. Similarly, now we are having edge cloud, a lot of edge cloud convergence. In fact, edge got a lot of momentum because of the cloud. And in edge cloud convergence, what we have the end devices, then we have edge, could have some fog devices as well, and then the cloud. So but you can do a lot of work has already been done. What you can do is you can have a culmination of other technologies like AI into this. So what you can do is you can do the dynamic task offloading. It's already been done. You know why the edge is there? Because they provide you ultra low latency. If you have to do some computation near to the end user, the cloud is far. So that is the reason you deploy the edge devices. You do the computation near to the user or near to the edge device, and then you could have the bandwidth constraints as well. Or in some specific case, you can have a privacy regulations as well. It could also create a need to have the edge devices, because there could be some certain privacy requirements in a certain region, especially Pakistan. We generally do not talk much about this one. Let's say you are living in USA. In USA, you do have different privacy regulation across states. So that creates a challenge. So what you can do is probably in that case, you can even use an edge device to comply to a certain privacy regulation into a certain region, rather than sending or storing that data onto the cloud. So this could be done. Or in terms of processing that data, for example, you could have a requirement like you cannot store open data into the cloud. So rather than sending that open data onto the cloud, what you're doing is you're implying the privacy onto the edge device and then sending that data onto the cloud. So you do have a lot of use cases for edge computing, like you do have autonomous vehicles, smart cities, industrial IoTs, AR, VR applications. So what are the challenges and the areas that you can actually cover? Application partitioning and placement. Like you can partition your application. Okay, application has been divided. An application in general in edge and cloud, once we talk about the vertical partitioning. Like some of the work has been done onto the cloud and some of the work has been done onto the edge device. But it can be a horizontal partitioning as well, where you partition application and it's been run onto multiple edge devices and the aggregated computation might be sent back to the cloud. Then a big challenge is state consistency across layers, and that stands again the same, like between cloud particularly and edge devices. And if you're using multiple edge to do the same computation, then you do have this challenge, like how you're going to ensure the data is the state of the data is consistent across different entities. Then resource heterogeneity, it always brings challenge, because the resources, they are of different types. They would be producing data in different formats. And then even we are talking about a lot of sensors as well. So sensors, they would be producing different types of data. Then fault tolerance in highly distributed system, like if you do have a bigger cloud and edge network, how you are going to tolerate the faults. And then security across multiple administrative domain, because the cloud is being administered by someone else and your edge is administered by someone else. So how you are going to assure the security and privacy concerns across these. Then because of edge and cloud, now both, we do have new research of like all these things that I discussed here. They have been there for the past 8-10 years. So we have been discussing these things. But now what are the new opportunities or new challenges? What you can do is you can do federated and distributed learning by utilizing the edge infrastructure, edge and cloud. So you can have this infrastructure, so you can do federated learning at the edge. So what you are going to do is, instead of sending all the data onto the cloud and the centralized cloud model is getting trained by having that data, you are doing that model training onto the edge. And after doing this model training, the model could send your weights and whatever are there required for later on doing the inferencing or decision making. So it's sending back it to the cloud. So the cloud gets all this aggregated data, because different edge, they could have different types of data requirements. But could be an edge model, like you could have edge computation onto your mobile towers. So you do have multiple mobile towers. There are passengers or there are cars which are passing by and they are sending some data. So someone is probably doing some monitoring of the traffic and doing the decision making. So you are training that model onto the local devices, onto the local edge nodes, and then sending these things there. Then privacy preserving AI model. Like I said, what you can do is you are adding noise to the model, because you do have that model running onto the local device, so you added noise over there. You drifted slightly your data, but in a way, it's once it's sent to the centralized node, there is not going to be an issue. And then you can have homomorphic encryption as well. Then collaborative intelligence across devices. What you can do is then you are running this model, so you do have now intelligence lying into different edge nodes, and you are doing the decision making there. So you have split computing and knowledge distillation. And then you can also have peer-to-peer learning as well. In the peer-to-peer learning model, these edge devices, they are going to do the computation, and then rather sending this data back to the cloud, they are going to talk to each other. And then they are going to aggregate this data together collaboratively in a peer-to-peer way and going to do further decision making. And then the models which can reduce data moment and latency. Another thing that we are talking about a lot these days is the quantum. It's been in hype since long. It's there because now you have commercial quantum computers available as well. And then cloud providers, they are also providing you quantum computation as well. That's why we are saying it quantum as a service. Quantum has specific use cases. Okay, many people, they think quantum as like it's some sort of a supercomputer, a new computation model. It's yes, it's a different computation model, and the major difference is what? Bits and qubits. So the qubit could be could have two values at the same time, like the bit has 0 and 1. Qubit could be in 0 and 1 at the same time. That brings challenges as well, and the quantum as a problem, quantum is highly prone to errors as compared to the normal computer. So that brings a lot of challenges as well. But we do have quantum as a service. Amazon is offering, Azure is offering, IBM is offering, and there would be many other offerings as well. So it's making it easier for the user to use it only for the time they can use it, which is a big opportunity for the users if someone wants to have the quantum computers available. So it's very difficult to have one because it's very expensive. And why it's very expensive? Because there is a lot of research being done. So the research cost is being divided on a very few units, which is a fundamental problem if you are going to have some supercomputers or such type of specialized computers. And there are a few models which are giving you ability to write code in standardized language, but they are not very well established. Most of the time, the programming onto the quantum is done using low-level languages specific for the quantum. And then there is hardware diversity as well, because different quantum computers, they are having too much different hardware. Whereas the general computer hardware that we use every day, they are quite standardized, where we do not have much differentiation in the server models. So we could have hybrid quantum classic workflows where the computation is done between the quantum computers and the classical computers. Again, yes, if you are using cloud-based, so there come some sort of challenges, but here we are talking about in a classical way. Like in general, quantum versus the traditional other classical computers. Like you can have workflows between quantum and the classical. And then what about HPC and AI pipelines? Because we are using a lot of AI. So what about that? Like if you are going to use the AI onto the quantum, is it good for that? Right now, quantum is widely being used, like for the physics simulation, for the scientific workloads. In computing, it's more right now being used in the cryptography with the mathematical function. We are using that. So with the high performance computing, we are going to know in future like how it's going to work for the traditional HPC workloads. But at the moment, yes, there are challenges related to if you are going to have a hybrid architecture where you are going to have regular workload working along with the quantum workloads. So scheduling quantum jobs with noisy hardware, because quantum has a noisy hardware. It's not error-free. Co-design of classical and quantum workflows, even like once you are running some job onto the quantum, it's not predictive. Like you're going to run it again, the result could be different. So that's the biggest challenge. So how you are going to design classical and quantum workflows together so that they can work together. Then abstraction layer for quantum programming. Like you can build a layer where you develop high-level programming language, or you customize a high-level programming language, which can work onto quantum computers. Like I said you before, currently most of the programming is done at the low level, which is, it's a bit challenging. And then performance modeling for hybrid systems, like how you are going to measure the performance once they work together and once they work independently, like you are running a certain workload. So how that workload is performing onto a classical quantum computing versus the other quantum computer. And since I told you that quantum behavior is unpredictable, so you are running a quantum computer, you are measuring its performance, the next time performance measure is going to be different. That's a challenge as well. Then sustainability and green cloud computing. We do have rapid growth of data center energy consumption. Too much energy consumption has been increased. Right now, we are using, data centers are using how much electricity? Anyone has an idea? Like how much electricity the data centers in the world they use in comparison to the world's total electricity need? It's around, there are different studies, it says around 2 to 3 or 4%. By 2030, it is expected to be around 13 to 15%. Why? Because of the AI. Because AI is increasing these workload and energy consumption requirements by large. So the total energy consumption of the world's data center is more than right now the United Kingdom, at least. In the whole country consumes, it's more than that, and they consume a lot of energy. Okay, in United States right now it's around 4 to 5%. The data center they consume this much energy, and again in the US the electricity consumption is very, very, very high. In Pakistan we do not have a lot of electricity consumption because there are very few devices which are run by electricity. What do we run with electricity? We just run these things like the lights, fans, and maybe some air conditioning. So air conditioning, it consumes a lot of power. But in the Western world, they run their kitchen onto the electricity, or most of the kitchen devices, they are electricity devices, and then all the others, they run onto electricity. There is a lesser consumption on the gases. Then carbon footprint of AI and large scale training. This is a big challenge, big challenge. Like I said, you could cloud computing. Why cloud computing is becoming, problem for the green? Because of the carbon footprint of AI in large scale training is high. You know what? Like I told you before, that cloud has given you an advantage, even in terms of green computing. Like, okay, you got the cloud. Before cloud, every large organization was running their own data centers. So a lot of their resources were wasted because they were required to have more resources than they were actually needed. Otherwise, they were not able to meet their workloads. So a lot of them, they were idle, or even if they are running, they were consuming a lot of energy. So in aggregation, they were more consuming more energy than what the cloud provider is consuming. Okay, let's say there are 100 companies which moved to the cloud, so the consumption, electricity consumption of 100 companies was much more than the cloud provider. The other thing was the appliances and the devices and all that. They were all also much more than owned by the companies as compared to the cloud. That was a good thing about the cloud. But what the cloud actually did with the passage of time, they got bigger and bigger and larger data centers. So these data centers are usually in some specific area. Whereas if we talk about those enterprises data center, they are scattered. So what the cloud is doing is they are in many cases harming a specific area in terms of carbon emission, in terms of bad green computing. Okay, so they are affecting a specific area, whereas these companies or these organizations, they were scattered around different areas, so they were damaging partially different areas, but the cloud is damaging some specific area. And now, like we are seeing that there is an explosion in terms of data center requirements, especially with the AI and all this. So this factor is going to increase by large, okay, because we are increasing this thing. So we are having energy consumption and all these problems associated with training and then inferencing, especially, like with the large language models, because it's very, very expensive in every terms to train your large language models. And then even doing the inferencing as well. What we generally think is, okay, it would be it's very expensive to train a large language model. It got trained. But what we are doing most of the time is we are doing the inferencing. We are asking ChatGPT, okay, tell us about this thing, tell us about that thing. So what is happening, one of your prompt is actually taking or consuming a lot of energy, okay, and creating or emitting a lot of carbon emissions. Okay, so model got trained, okay, it might stay for a long time, but you are doing a lot of these things. And then, so you might need to do carbon aware scheduling. Like I told you, okay, a cloud provider might be sending the workload to another area which is consuming renewable energy resources, so that the carbon footprint could be decreased. But that brings other challenges, like I told you, the workloads could become far from the actual users, and that might increase the latency and the problem. And then model compression. What you can do is you can build lightweight models so that your carbon footprint that can be decreased. Right now we are also talking about large language models onto the edge devices as well. So you can have that thing. Sustainability is a core research goal. You should have a lot of focus on to sustainability, because earlier we were used to have, once we are conducting a research, what we were used to have: cost, performance, efficiency, latency. These were usually the parameters which we were used to talk about. But now the world is too much aware about this sustainability issues, so you need to consider these issues as well. Once you are going to develop a model, this should be energy efficient as well. Any model, I'm not talking about, okay, AI model, any algorithm, any procedure, any mechanism to solve some certain tasks. So they should be good. So you should have software defined sustainability green code. So your algorithms, your codes, this should be green, okay? And this is very important. I think we should teach this thing to our students as well. Like I usually talk about a lot about performance codes. So if you're writing performance code, that also brings this green computing as well. We do a lot of casual coding, which I have seen. Most of our programmers, they write code in a way which can be easily optimized to run in less than half time. Less than half time. This I'm saying it very casually, because it could be way more than that. Okay. And then life cycle assessment include not only electricity, but also, what is happening for the past 2-3 years? We are talking about this thing. Electricity, okay, this was the green impact and all that. But now we are talking about what? We are talking about the minerals, the materials. Okay, we got out of the silicon, so we got a silicon chip problem. So we dig all these sands and from the whole world, and now we are having a lot of race, like this universal race going outside the planet, reaching to the other planets. What is one of the major reason is materials. Okay, the first material, very precious material that comes in our mind, what is that? We normally talk about oils, we talk about oil. Oil may no longer be a much precious thing, maybe in 30, 40 years, because, in terms of, because why we are using oil? To run the things, to run the cars, to run the factories, to run the infrastructures, how? Either directly or indirectly through electricity. So actually we need electricity. If we talk about the cars, they are already onto electricity. Our factories and other infrastructure are already onto the electricity. So electricity can be produced from the renewable energy sources. You could have other resources. Okay, so we could have a problem. But now, where we are competing now? In the materials, to produce the chips, to produce the devices and all that. So that's a challenge as well. So we need to do, once you are going to build any model, anything, any product, you should do this. This is a very important aspect, this sustainability. Okay, so you need to have this life cycle assessment, and then you could have circular or modular hardware as well. With the circular, okay, you can reiterate, but your service should be too much modular, so that if there is some specific area which needs more improvement, you should just change that thing. Yes, right now we still have some modular structure, but it needs to be improved more. For example, with the new generations of the servers, we often get a problem in terms of communication interfacing, in terms of the speed or of the buses and all that. So this needs to get improved. Yes, you do have some questions.
Can you tell me other materials other than silicon?
You have platinum, you use that gold, because in the processor construction you use the gold as well. Like
The cost,
I'm not sure about the cost. Cost is not the problem, because what you're doing is you are doing a lot of productivity. The money generation is there, so you can afford that thing. The problem is the scarcity of those materials, because what we are doing is, sorry?
Are these other materials are available to the masses, like standard chips that is built in on top of the platinum or something else?
We could have that, but like silicon, if you talk about the silicon, it was a very cheap material because we were used to get it from the sand. But the problem is we dug all the sand. We are trying to dig all the sand from all the world. So that is creating a problem because it's limited, it's fixed. The same is with the oil as well. So because we are getting the oil, so price probably would not be a big problem, because the world is expanding in terms of money generation and the wealth generation. So that might not be a problem, because you are in that cycle. You are generating money, you're generating wealth. And then if someone has more money, other one is going to be deprived. So someone has the money, so they are going to buy it. The problem is the scarcity, because the resources are limited. The only resource that is not limited is the renewable resource. Anything which is consumable, so you have the problem. That's why a lot of work right now has been done in recycling of these materials. Like, you should recycle these materials, and you cannot recycle every material and cannot recycle 100% as well. But a lot of work has been done into this aspect as well.
I think so. On my side, the sustainability is a very difficult challenge to actually opt with.
Yes.
I think so.
The first thing with the sustainability is there is a cost.
Right.
If you want to make the thing sustainable, there is a cost. You go for the green computing, there is a cost. You imply standards, there is a cost. And you have seen that.
If you think about it at a bigger scale, how are you going to measure this?
The first thing is the governments. Governments, they have to play their role, and they play their role. But it depends upon which country. Like, if I talk about right now, the Europe, they are very strict into this. Like Europe, they strictly follow their sustainability standards in every aspect. It's not limited to computing. It's also the other areas where, like, we talk about the factories and the other industrial units. So they emission a lot of things that they do have very strong enforcement. Once you talk about the United States, yes, they advocate to the whole world, but there is a question mark, like how much they follow this. And recently you have seen, like, they actually signed out of this environmental pact. I forgot its name, which was the globest. Similar stands for the China as well, because the China is not that much good with that. And right now China is producing a lot of emission to the world. So that's a problem. And then there comes the countries like which are the developing countries. So in the early stages, if they have some sort of a strength and then they can compete or they can stand in front of the countries who have already violated these things and now they are good guys and they are behaving like to be a good guy, they can sustain, like India, Brazil, or other countries. Even we could sustain, but it's challenging. It's challenging, and then everyone has to play their role. That's a big problem. You know, the biggest problem with this one is the human survival. That's a problem, and we have already starting seeing the impact of this thing in terms of climate change, and it's disruptive. It's happening everywhere because, okay, like we see it, we are getting more affected probably at the moment, but you can see the global impact in the coming years. In 30, 40 years, the earth is going to be really, really very different. That's a problem. So sustainability goals are very important. That's why I'm saying, like, if you are writing your code, it should be green code. So if you are doing scheduling, then it should be carbon aware workload scheduling, energy efficient hardwares and accelerators, then renewable power data centers, geo-distributed load shifting, and then metrics for carbon and energy transportation. Metrics, with the metrics, there is also a problem because they right now use PUE, power under equipment or something, a matrix which they generally use to measure. And there are a lot of criticism that this is one parameter, how you use this. So there's a lot of need even in this area to come up with new parameters to estimate the energy impacts. Similarly, geo-distribution of the load shifting, what I told you before, like you can shift your workloads from one place to another. Then renewable power data center, more and more renewable power data center. You know, even what has happened with this blockchain, because the blockchains initially, once they came, they were used to consume a lot of electricity, and still they use a lot of electricity. So there were miners who were getting reward, but they might be consuming more energy than what the reward they are going to get. So they got an emergence in terms of deploying the data center. Like the people, they started deploying data center in the area where they have the renewable energy sources. Like you might have seen the example of Bhutan. Bhutan have taken a national policy and they have deployed a lot of blockchain or these cryptocurrency rigs to mine the blockchains there, because they have a lot of water available through the mountains. And then you should have energy efficient hardware, and there have been a lot of work in this area, that your hardware should be efficient. And but every day we are coming with the new requirements. With the traditional hardware, you are making it energy efficient, and suddenly there is a new spike, like you got these neural processing unit and tensor processing unit. I'm not sure about like what's the energy consumption of TPU versus a GPU. But if I see like TPU are specific purpose, so they might be consuming more energy. They might be, I'm not sure about it, because they are built for specific purpose. So in this race, in this global race of getting the supremacy in terms of offering the artificial intelligence or the machine learning services, someone might be affecting that thing, like providing a better performance in terms of the response time and in terms of hardware cost, but might be producing more energy.
Dr. Sir, will you compare quantum computing with green computing? What do you say about that?
They are quite different, because green computing means like you are looking at the sustainability goals. Quantum computing is specific. I'm not sure about like how much energy it consumes, or
I know from some of the researchers that the quantum computing itself require a minus
50.
-50 centigrade to be cooled down. The computer should be cooled down at
I'm
that
not
level.
sure about it, but if I talk about the data centers, they do have a variety of types of cooling. They do have air cooling, like air conditioning installed there, but they also have water cooling as well. And you might have seen like even the home computers, like with the GPUs coming with the high-end GPUs, a lot of young kids, they play video games onto them, and they are pretty expensive. Like you can buy in $8,000 to $10,000. They come with the water cooling, so the water is circulated with, okay, it's the home. But once these cloud providers, they build their data center, it's a very common practice to build near to some water streams, because they get the water from there and they send it back to the streams, which is also an environmental hazard as well. But I'm not sure about the quantum computers. Okay, so you do not have some standardization in terms of sustainability matrices. Trade-offs between performance and energy, what are they? How you can do these trade-offs. Similarly, incentive alignment across providers and users, like if you want to incentivize, how you are going to do it with the provider and the user. Like you see, a lot of countries right now, they are giving incentive if you are shifting on to electrical vehicles. So same thing can happen here, but who is shifting right now? We are talking about the cloud. So there is cloud and then there is a cloud user. So who you are going to incentivize? Because a cloud provider, like I said you before, sustainability has a cost. You have to decompose the materials, you have a cost. So a cloud provider might be a little bit more expensive if they are applying the incentive, these things. So the government might offer them electricity at a cheaper cost because they are using some more energy efficient hardware. Similarly, a user who is moving on to the cloud, they might have to pay a bit more. For example, if the cloud is charging them more because they have more cost, but the government or tax agencies or anyone might be incentivizing them in any terms, like in terms of tax or any other thing, because they are running their workloads onto energy efficient clouds. And then you can have regulatory and reporting requirements as well, like how they are going to be reported and what sort of regulations are going to be applied onto that. Then we do have security and privacy challenges in our next generation cloud. Like our threat landscape is changing. It's changing by fast because we have massive increase in the infrastructure. It's not only cloud, it's about edge infrastructure, it's about IoT infrastructure. Your air conditioning is connected to the internet, which was not used to be. Your television is connected to the internet. You do not know what is happening around. So threat landscape is increasing. Your car is connected, unfortunately. It's the moving death. Okay, so someone can hack your car and can do anything with that. And then you have multi-tenancy and multi-cloud complexity. You can have your infrastructure across cloud, and even if you are on a certain cloud, it's multi-tenant. There are multiple organizations or people or the users who are using the same infrastructure, so there are challenges. And edge nodes, now you are talking about that, why not to do the computation onto the edge devices, which might be operated by the third party. So this is a new attack surface. So the people, they can attack your edge. And the other problem, you see, we were talking about the learning onto your edge nodes. What about if someone attacks onto that and they mutate the data, and the data that you are getting back onto the cloud has been mutated? You know, like cloud provides you a lot of security layers. Edge is obviously not going to provide you that many security layers. Cloud is operated by some very large scale vendors with a lot of money, a lot of resources. So they have invested a lot, and whatever they invest in terms of security, they are going to get its share by a lot of users, a large number of their user base. Whereas in comparison to that, the edge, there are going to be a lot of edge providers, edge service providers. The first thing is the edge equipment. Okay, it might be coming from specific vendors, but edge providers, who could be the edge providers, like your mobile telco. One of the biggest future market for the mobile telco provider is the edge computation, is the edge, because they do not have any money any longer in telephony. They do not have any money. What they are earning right now is a bit earning is in the data networks, in the data, and again in the data it's very competitive. So almost all the mobile companies, they are trying to bring applications. They have become like software houses, software companies, to bring application, to do some sort of research into the use cases through which they can enable your edge computing. So this is a new challenge. And then AI driven attacks and defenses, because AI has given a lot of power. Even, you know, like what's happening right now with the AI, it has become very easy to hack anything, because okay, you just write especially with generative AI, write a prompt, ask how to hack my friend's computer. It's going to tell you a lot of tricks, because starting from the social engineering to other things, how to hack a Wi-Fi password. Even it's going to give you, okay, you can get guidelines from the Google as well, but it's going to tell you very good, not only the guidelines, it's going to provide you the code as well, and the scripts as well. So you're going to get a lot of help. You can try it today. And then other emerging security trends, like you have zero trust cloud architecture. You're not going to trust onto the cloud. You do have zero trust. So then confidential computing, there is a problem. There are a lot of tenants. We say cloud is too much secure. Yes, it's secure. We have a lot of security layers. And how do we provide the security? Through various layers, through networking, through security enforcement, a lot. It's much more than, if you remember, we have last year bootcamp. Remember, we talked about the security in the network, and there were many layers of defenses. But eventually, these workloads, they are going to run onto physical hardware, which is going to host it from multiple users. So what you can have is, at the processor level, you can have an attack. Not at the application layer, not at the operating system layer, at the processor layer. Two applications are running from two different users parallel onto the same processor into two different cores. So in the cache or other areas you have, and that area is called confidential computing, because you can have problem into that area. And then what you can do is, in order to do the confidential computing, you can have homomorphic encryption and secure enclaves. Samir is working into this area in the homomorphic encryption, where you actually encrypt your data. Which data? On the registers. If you are going to perform addition onto the data will be encrypted. It means its meaning has been changed. I mean, its value has been changed. So what the homomorphic encryption does is, if you're going to provide the add operation, it's going to add them, and once you are going to decrypt it, it's going to exactly the same answer what was required. And it's challenging, obviously, it requires more smartness. But it keeps it that, like, but eventually once you are going to send it back onto something, so it needs to get decrypted. So AI driven threat detection, so you can have that, like you are using AI to launch attacks, and you can use AI to do the threat detection. Another our student, Ms. Atika, is working on to this, where she is working on zero-day attack and adversarial attacks. And then we can also have blockchain-based trust frameworks. Ms. Ikra is working into this, where she's building a trust framework with a decentralized blockchain. Then you can have verifiable security guarantees. Then you might need to balance cryptographic strength with performance. It's always been a challenge. Like you are coming up with the newer encryption algorithms, but they are consuming a lot of computational power. And computational power then means energy consumption and all that, and the costs. And then secure AI models and pipelines. AI, is it itself secure or not? Okay, because with the large use of AI, you also have a new surface, which is AI itself. AI models, are they secure once you are doing something? And then cross cloud and cross border trust management. Okay, cross cloud, how you are going to trust different clouds, and then cross border, once your data goes from one place to another place, how it's going to be secure. And then next generation cloud architectures, it's no longer virtual machines. We do have what? We already have serverless computation being done. We do have containers. We do have function as a service, and so we do a lot of such things. Then we have stateful and long running serverless functions, like on Amazon we run it for 15 minutes. Then you do have fine-grained resource isolations. Your resources, they are isolated from each other. And then you do have event-driven cloud platform as well, which runs according to the events. Like we do have queuing services, we have notification services, and then function as a service as well. Then we do have separation of compute, memory, storage, and accelerators. Obviously, they bring new challenges once we have them separately, because what is the backbone of a computation in terms of hardware? Once we are doing it, it's the main board or the motherboard, once you're doing in a single computer. But once you make these things separate, like compute is separate, memory pools are separate, storage and accelerators, they are separate because they are lying in different areas. So now the backbone is the network. Okay, network becomes the backbone control plane of this. So then you have network attached resources. All of these different types of resources, they are network attached. So this could be a active research area, like how you're going to do this, how you're going to improve their performances. and then on-demand composition of hardware. Because many cloud providers, they come equipped with the fixed type of hardware. Okay, this type of machine, this type of machine. Even though they give you a lot of variety, but what we can have is we can have on-demand composition of hardware based on our need. And then even you can have AI-driven composition as well, where the AI predicts, okay, how much you need in future or how much is the requirement. And then improved utilization and flexibility. Next, then if we talk about the network, then on that side we have software-defined networking. In the cloud, we already do the software-defined network. Even all of our network is, we configure the network onto the cloud, but that is software-defined. We do not have to configure any physical hardware. Then we have smart network interface cards and the data processing units. We have also programmable data planes as well. Like we do have the data lakes and other things which are programmable. We get the data, we get the ingestions from different variety of resources, we process them, we run the analytics, we put them onto other planes as well. And then we have low latency interconnect for distributed AI as well. Then socio-economic and ethical dimensions are there. We have democratization of computing power. This is a challenge as well. You know, with the emergence of AI, now there is another digital divide. Okay, there is a digital divide, because if you cannot afford the GPUs, you are in trouble in future. You see, right now a lot of work in the computation domain or computing domain is done in the area of AI. If you go back a few years back, a lot of your work, if I talk about the IT industry, a lot of your work was not in AI, it was mainly in the traditional systems with some analytics and all that. So that was requiring just your computer. You can have a very cheap computer, $400, $500, $800, $1,000 computers, and that was okay. But now with the AI, now you need the GPUs. So the GPUs are not widely available, particularly in developing countries. So this is now a new digital divide as well. Cloud provides you that thing, so it democratizes that thing and gives you accessibility to these very expensive resources on pay as you use. So but this challenge is increasing without that, and so you are having this digital divide and equitable access issue. Then data sovereignty and governance issues, because where the data is going to lie, that's always been a challenge, and that is going to be a challenge. And now we are not talking about the cloud. You know, earlier we were on cloud, local infrastructure. Now we are talking about IoTs. We are talking about edge devices, fog computing. So where the data is, from where you are getting the data, what are the rules, who is going to govern, what happens if there is a data leak at some other issue. So that's a problem. And then ethical AI in the cloud platforms. Next. Okay, similarly, regulatory and policy considerations are there, like cross-border data flows. If your data flows from one border to another, which laws applies onto that? Europe has worked a lot onto this, and they have this advantage, like they already have European Union, so they have standardized law usually, which applies onto their data. Okay, so they do have these GPDR rules, so they apply those rules. In comparison to that, in the United States, they do have problems. In South Asia, Central Asia, we do have a lot of problems, or even in the Asia Pacific, because every country, they have different rules and laws regarding to that. So that stands for everything, for compliance, for auditing, then for AI governance. Right now, we're talking a lot about the ethical AI. What is ethical AI? How much AI should we use? What AI can do? And Europe, I think, recently has released a framework for an ethical AI. And then role of standard bodies and government, what role they can play, whether they can be just guide as a guidance, or they can be a regulator as well. So the future vision is, like, we are going to have more autonomous cloud ecosystem rather than based on some fixed or rule-based decision making, more AI-driven cloud systems, intelligent digital twins, a lot of technologies, they are getting merged within that. Programmable meta cloud, we are going to have a lot of even tiny clouds as well. You know, even there is a concept of cloud on chip as well. And then seamless integration of cloud, edge, AI, sustainable infrastructure, and possibly with the quantum as well. Quantum is not an essential thing. Don't take it as a regular mainstream thing. But yes, quantum is emerging, so you might have seen a lot of things. So what are the open research questions? All of them, they were the questions, like they are the areas where you can think about it. And how do we design explainable autonomous cloud? Like we are building autonomous clouds. We will talk about autonomous cloud, but are they going to be explainable as well? Predictable, reliable? What programming models unify edge, cloud, and quantum computing? How we are going to have this integration of quantum with the edge and with the cloud? How can sustainability be enforced by design? Or how we can achieve these sustainability targets? How do we build globally trustworthy cloud systems as well? So there are implications for academia and industry both. So we do have a lot of interdisciplinary research direction, and that is one of the reason, if you know, like I've been emphasizing a lot, because cloud is not cloud. Cloud is how we do the computation these days. Many people, they think it like, okay, cloud is something specific. Like, okay, blockchain is blockchain. Okay, AI is AI. But the cloud is how we do the computation these days. It's the advanced computing models. We are talking about large scale infrastructure, and it's doing everything. So once you talk about the AI, but once you talk about AI on the cloud, it might be bringing new challenges as well. So, or AI on a large scale shared infrastructure, I would rather say, rather than naming it as cloud. So you do have those issues. So there are a lot of research challenges. And what I was saying, like I have been emphasizing a lot in the past couple of years, like if you're working in the AI, you're working in the security, try to have an amalgamation of these things. AI is really application oriented. So we have been emphasizing, like rather than applying it into the external domains, like in the medical or other domains, why not to apply it within computing domains? You see, like a lot of work has been done right now. AI is there, you're using AI, so there are challenges onto the cloud, because cloud is now the major enabler for AI. Okay, so once you are going to use the cloud, so there are research challenges. Then what AI can bring, there is a research challenge. So there are a lot of issues related to AI. And then need for real world experimentation platforms, collaboration with industry and policymaker is obviously required, because there are a lot of challenges related to data, related to the AI, related to the governance and sustainability. And then eventually in the academia, curriculum evolution in cloud systems and advanced computing research. We need to evolve the infrastructure, and that's one of the problem which we see is a student being taught by a student in 1980s, taught another student the same curriculum in 2000, taught another student the same curriculum in 2020, is teaching here the same curriculum which was taught in 1980 with the same perspective. It's not about the programming is same, nothing been changed, but the approach should be changed. Okay, there was no quantum cloud as infrastructure, because you're building off of that. If you do not have an idea about it, you do not have an understanding how the things they are happening in the real world, then there is a big problem. Okay, you do not have an understanding of how, because right now we do the DevOps approach. We work with the CI/CD pipelines. This is how the softwares are engineered. They're not engineered how the Roger Pressman have been telling you for past 30 years. Yes, his book is best-selling. Okay, so but this is how the softwares are engineered. So that brings new challenge. So implication for industries, they do have competitive advantage, obviously, through the cloud, and now would be with the intelligent clouds. Operational efficiency and sustainability could be there. Security could be a differentiator. It could be provision, or it could be a challenge as well. And then what the cloud has done, rapid innovation cycles with higher complexity. Cloud has enabled a lot of startups, a lot of new companies to handle the needs and to become successful. Cloud has a lot of success stories for that. So the key takeaway for today's discussion is, like, cloud is evolving into distributed intelligent ecosystem, providing a lot of facilities, particularly related to intelligent, itself intelligent, and providing you intelligence. These are two different things. Okay, cloud is evolving itself as intelligent, doing intelligent decision making and all that for its own sake and for the customer and for the client, but also providing intelligence services as well. Now, cloud is the biggest platform providing you the intelligence services. You have the Google AI and machine learning, a a lot of their services are now, which are being now used, are AI and machine learning services. Same is for Amazon, same is for IBM, same is for Microsoft. So your research is driving towards autonomy, sustainability, security, and newer architecture. Yeah, we feel it, I don't know, somehow, while a bit less than important, we talk more about autonomy, security, new architecture. So the future of computing lies beyond only this traditional cloud. We're not talking about, that's why I always say it, advanced computing. Now it's amalgamation of all these things, IoTs, edge, quantum, cloud, everything. Thank you, Jay.